In this lecture, we're going to talk about the analysis of chemical compounds. As you can see from the title slide, there's going to be similarities between this topic and our lecture on the analysis for the presence of different elements. But even though there are some similarities, as we'll see, there are also enormous differences between looking for elements and looking for compounds. So under what circumstances might we want to analyze a sample for the presence of chemical compounds? Well, as you'll see in the lecture on fibers later, one of the important things you need to do when you have a fiber sample is to determine what that fiber is made of. So you have to analyze the compounds that make up the fiber in order to identify it. In addition, because most fibers are colored, you might want to analyze the dye to find out what compounds are present in the dye. As you all know, at major sporting events, the blood or urine of athletes is routinely tested for the presence of unauthorized substances. And this is another example of where we would want to analyze for particular compounds. And one of the major applications of this kind of chemistry is in the analysis of suspected illegal drugs. And these suspected illegal drugs might actually be the material itself, or it might be analyzing body fluids from a suspect, an alleged user, for the presence of those illegal drugs. So analysis of compounds is a very important part of forensic science. A complication in the analysis of compounds, which we did not encounter in the analysis of elements, is the fact that the samples that are being given for analysis are actually very complex mixtures. If you think, for instance, of a blood sample or a urine sample, there are a huge number of different compounds within that sample, and most of them are quite innocuous. They're quite supposed to be there. Urine, for instance, contains all the byproducts of our metabolism. And the forensic scientist will be analyzing that very, very complex mixture for maybe just a few or even one compound that is of interest. So when we're talking about the analysis of compounds, there's really two different things that we have to talk about. The first thing is how to separate out this mixture so we can find within it the compound or compounds of interest. Only when that has been done, we then have to identify the compound and find what it is. The main method that we use for separating a mixture into its different components is chromatography. And there are many different kinds of chromatography, but they are all based on the same principle. So in chromatography, we have what is called a stationary phase. And this is an inert absorbent material. And it can be anything from paper through to silica. And we have a sample. And the sample is applied at one position in the stationary phase. And it's indicated here by the purple bar. We then need to have our mobile phase. And our mobile phase is either a liquid or a gas, and that flows through the stationary phase. And as the mobile phase flows through the stationary phase, the components of the mixture that we're trying to analyze also flow through. So as we run the experiment, as time goes by, our mixture will separate out into its individual components based on the speed with which they move through the medium. And as we run the experiment longer, the separation will get greater. And of course, one of these components will get to the end of our stationary phase well before the other one. And we've now separated our mixture into its different components, and we could go ahead with whatever analysis we're going to use to identify them. There are many different kinds of chromatography. The simplest, easiest, and cheapest one is a technique called thin layer chromatography. So for thin layer chromatography, we need a TLC plate. And the TLC plate consists very simply of an inert backing plate, which is typically glass, but can also be other materials such as aluminium or plastic. And that is coated with our stationary phase. a thin layer of an absorbent material, and it's most commonly silica. It's sometimes alumina or some other material. The great thing about TLC is that the equipment you need is very, very simple. You need a jar which contains the mobile phase. You can use a jam jar. This isn't a jam jar. You need a fine glass tube, that is a capillary. This is for applying the sample. You need a pencil, a pair of tweezers or forceps, and most important, a TLC plate. So this is a glass-backed TLC plate, and this side has the stationary phase, which is silica. So what I do, draw a line on the TLC plate to show where my sample is going to start. And as a sample, I've chosen this one, and that's because all the components are colored, and we'll be able to see them at the end of the experiment. We take up some sample into the capillary. Apply it to the TLC plate where we've drawn the line. We can then put it in the jar. And then we wait while the mobile phase travels up the plate. Okay, when the mobile phase has almost got to the top of the TLC plate, we can take it out of the jar. Make a mark with the pencil to show where the solvent got to. That is the so-called solvent front. And then you can see the result. We can clearly see that this sample contains two components, or at least it contains two components that are colored and we can see under visible light. So when we are working with colored compounds, you can just see by inspection, just by looking at the plate, you can see where the spots are. But most organic compounds are not colored. They are colorless. So you can't see them just using your naked eye. So there's a whole range of techniques for making these spots show up so that you can see them. The simplest one, which works for a lot of compounds, is simply to put the TLC plate under a UV light, and then the spots fluoresce, and you can see these purple spots on this green background under a very simple UV light. If your spots don't show up under UV light, then we have a whole series of chemical reagents that we can apply to the plate, and that will make these otherwise invisible spots show up as colored spots. So here's a typical TLC plate. It's visualized under UV light, and our unknown mixture that we're analyzing is lane C. And as you can see, the TLC of lane C shows two spots. So probably there's two compounds in here. Now, we're comparing lane C to two known standard compounds. So compound A, compound B, we know what they are, we have spotted them on the TLC plate, and we can see that the two spots in lane C correspond to compounds A and B. Does this mean that we can use TLC as a technique for identifying compounds? The answer to that question is not straightforward, because TLC is what we call a presumptive test. Now, a presumptive test is a test that cannot give you a definitive answer. Why is this? We are analyzing this mixture for its composition in terms of organic compounds. There are several million organic compounds that have been made, that have been described, that have been reported. Our TLC plate is only a few centimeters long. So it's absolutely impossible for a little TLC plate to separate and distinguish between all of those millions and millions of compounds. And it's frustratingly frequent that we find that two different compounds will actually give the same spot on a TLC plate. That is, when we run our TLC plate, those two compounds will move to the same distance. So when we do a TLC and we see that a spot in our unknown mixture corresponds to one of our standards, as it does in this TLC plate, we cannot say that that standard compound is present in the mixture. That would be a definitive answer which we cannot give. We can say that that compound may be in the mixture, and therefore we should go on to do further tests to determine this. So TLC is nice, it's simple, it's quick, it's cheap, but it cannot in all cases give you a definitive answer. Okay, let's look a little more closely at TLC. So here we have a TLC plate on the left where we have three standard compounds, the pink compound, the grey compound and the green compound, and we have an unknown mixture symbolized by the black dot. So suppose when we take this TLC plate and we run it, and maybe we get a result like the one on the right, where the solvent has flowed up to the position marked solvent front. And we can see the three standard compounds have moved, and our unknown mixture has now separated into 4 different spots. So there's presumably, probably, 4 components in our unknown mixture. Well, we can see that the green standard corresponds to a spot in the mixture. So we can say probably the green compound is there. The black standard compound also matches a spot in the mixture. So we can say probably or possibly that compound is in the mixture. The pink standard compound, you can see, does not correspond to any spot in the mixture. So now we can be quite clear. We can say that that pink compound is not present in this mixture that we're analyzing. At least it's not present within the sensitivity of this particular technique. But here we can also see 2 other spots have appeared. There's a yellow spot and a red spot. These are not matching any of our standards. So we can say that this unknown mixture contains at least 2 more compounds, and we have no idea what they might even be. Now, when we're discussing TLC, it's not good enough to say, oh, the spot up there or the spot down there. What we really need is some numerical method to describe the positions of the spots. And what we use is a number called the RF, which is the retention factor. And the RF is very simple to calculate. You measure the distance moved by the solvent on the TLC plate, we'll call that Y, and you measure the distance moved by the spot, and we measure to the center of the spot, and we call this distance X. Then the RF of that particular compound is defined as X divided by Y. So there's TLC, a very simple, very easy to do technique, but not quite accurate enough for our purposes.